Hey everybody, it's Buck Joffrey here with Sapio with Buck Joffrey. Today I want to talk to you about something pretty serious, and that is cancer. Now, more than 1/3 of people will have a diagnosis of cancer in their lives. And of the greater than 100 cancers that we know about, there are only about 5 recommended screening tests. Yet, greater than 70% of the cancer deaths out there are from cancers without any recommended screening options at all. But there is a new hope in our battle with cancer. It's a company called GRAIL, and GRAIL now has a simple blood test that can detect over 50 different cancers at early stages. Now, the test itself is called Galleri. And in this week's episode of Sapio with Buck Joffrey, I speak to Dr. Josh Ofman, MD, who's president of GRAIL, about this technology. Josh is a gastroenterologist by training and also has a master's in public health. I like that. He's a doctor, and it gives us that kind of perspective. I have to tell you that I personally believe this technology is potentially a major advancement for human longevity because of its ability to detect so many cancers at early stages. Just to give you an example, most pancreatic cancers are asymptomatic until it's too late. You may know somebody in this boat where literally they get a diagnosis, nothing wrong with them at all. 3 months later, they're dead. Galleri is showing that it can detect these types of cancers at its earliest stages, and that is blowing surgical oncologists away. But the Galleri is not without its critics, and even some oncologists voiced their concerns. Nevertheless, this is something that you're definitely going to want to know about and not want to miss. It could save your life.
In pursuit of health and wisdom, Sapio with Buck Joffrey.
Here with Dr. Joshua Ofman. Josh, welcome to the show.
It's my pleasure to be here. Thanks for having me.
So I want to start out just with some well, first of all, let's do this. Why don't you tell us a little bit about yourself? Obviously, I did a little introduction of you already on the show, but tell us how you're a gastroenterologist. How did you end up where you are now?
Well, it's a great question. So I did my undergraduate degree at Berkeley, and I was very interested in the history and philosophy of science. And so I got very into, how you begin to study technology and how you better understand its utility and the value that it provides, to society. When I went to medical school, I got very interested in gastroenterology as a field. I did that as my training at UCLA, and I became a gastroenterologist. But I did my postdoc, basically a postgraduate degree at the Rand Corporation, again, studying technology. And how do you, from a very scientific medical sense, understand the value of technology to an individual, to society, to the healthcare system? And I spent about 7 years in academia doing that across all fields, like just any kind of new technology in healthcare. How do you evaluate it? How do you assess its value? And after doing that for quite some time, I started getting recruited by life sciences companies who were actually developing this type of technology. And I ended up going to Amgen, which was a biotechnology company, because I kind of felt that's where the puck is going. Back in early 2000s, biotechnology was just coming into its own. And I really wanted to try to skate, to where the puck was going, and joined Amgen and spent 16 incredible years there in a number of different roles. And then when I was able to retire from Amgen at the age of 55, again, I thought to myself, where's the puck going now? And I got very interested in the relationship between human genomics and machine learning as a way of finding diseases. And I joined GRAIL.
Fantastic. Well, we're going to talk in a fair amount of detail about this test that GRAIL has called Galleri, which is really significant potentially in terms of improving human longevity and health span and all that kind of thing. But before we get into that, the test is related to cancer, and it's related to detecting early cancer. I thought it would be useful for people who really don't know that much about the biology here. is just to give a little bit of relevant background in terms of cancer biology, so we're on the same page. Obviously, you and I are both physicians, but let's start with some of the basics. Like, what exactly is cancer in the first place?
So cancer really is a disease of the genome. And, it really is very much related to the genetics and the heritability of your DNA. But it is really uncontrolled cellular growth. And there's a number of reasons, many, many different reasons why cells will grow in an uncontrolled way that become cancerous. But generally, in many of them, they're related to the genomics. Now, what we've learned about genomics is it's not just the code of the genome, right? So your DNA is made of a code of 4 nucleotides. But what we're learning now is that there are molecules that attach to the DNA that regulate the genetic code, and they turn genes on and off.
Right,
And
and
we
that's
know
referred often by as epigenetics, right?
that
The
that's
people
exactly
talk
right.
about the genetics being the part that maybe codes the actual, protein itself, and then you have the epigenetics, which is the material around that, around those sequences, which before, frankly, we didn't think much of, right? And now we're figuring out that they actually do mean something.
Buck, that's exactly right. And so when we say, interrogating the genome, learning about the genome, it's a disease of the genome. That includes the code of the genome and all the things that are attached to the genome, like, these molecules that we call methylation molecules or methyl groups that attach to the genome that turn tumor promoter genes on, they turn tumor suppressor genes off, and they do that across many, many different kinds of cancer. And so they're very related to cancer and the development of cancer.
Right. And so one of the things I want to kind of, and this will lead into the test later, but each one of these potential cancers and the mix of the genomic sequences, the mutations there's, and the epigenetics, these methylation points in the epigenome, they lead to essentially various types of fingerprints, right? And these fingerprints are basically kind of what we're looking at when we start looking at potential early detection. Is that correct?
That's right. So most genetic tests up till recently have focused on mutations, right? Changes in the code of the DNA. And many of them are associated with cancer. But again, for people like myself who are over the age of 50, I have many mutations in my genome that are similar and the same as cancer patients have, but I don't have cancer. So these cancer mutations are uncommon. Some of them are very important for cancer, but some of them are also shared by people who don't have cancer. So they're not always, they're important to know about if you're diagnosed with cancer. Do you carry this mutation or that mutation? Because it can tell you a lot about the cancer and its potential treatments, but they're not great ways to find cancer because they're uncommon and they often also exist in people without cancer.
One of the interesting things that I think people don't know, and maybe you can comment on this a little bit since you're in this space, is that cancer cells, it's not uncommon for cancer cells to exist within healthy human beings, but we have something called the immune system, obviously, that's constantly surveilling our bodies, right? And if you want to talk a little bit about, how that function works, that might be useful as well, because there is this idea that maybe you have cancer cells, but you don't have cancer. So what's the difference there?
Well, it's a great point, and we're on the early innings of really understanding that interaction. We do know that our immune system is surveying the body all the time and does have the ability to kind of shut down early cancerous growths. The extent to which that happens, where it happens, when it happens, and why it happens is something that we're still beginning to understand. But we do know that the immune system plays a really important role in what we call immune surveillance of cancer. But we also know that our prior understanding of cancer is less than complete. And we are now, by looking at the biology of cancer, like the DNA from cancer cells that we see in the blood, the immune signatures that we see in the blood, we're learning all kinds of new things about cancer now. For example, the old way that we used to stage cancer is pretty crude relative to looking at the biology of cancer by looking at its DNA, and those signatures are much more sophisticated. And as a result, we're learning different things about the natural history of cancer. So there's still, it's early days still, and we're learning quite a lot. But we know that even single cancer cells in circulation, when you can find them, are very informative and may signify that you do have a cancer brewing. And it's very hard right now for us to know whether these early signs of cancer are mean that the immune system is mounting a response that's going to shut down the cancer, or whether you actually have an early cancer that is going to be slow growing or fast growing.
Right, right. So, in the big picture, obviously we know cancer is a big killer. We know cardiovascular disease is typically the number one cause. We've talked on our show about how we don't even think that should be in the top 10 anymore with what we know. But now with cancer, it's obviously very common. Just give us some statistics on this. Like, what percentage of people develop cancer in their lives?
So I think it's somewhere between 40 and 50% of men and women will develop a cancer in their lifetime. It's very high. We know that cancer is soon to become the number one killer of men and women worldwide. Right now, it's ranked number two, but I think the epidemiology suggests it's going to overtake cardiovascular disease very shortly. And why is that? Why is it such a killer? It's because we're finding most cancer too late, when it's already spread, symptoms are present, and there are very few treatment options. So we know one of the only ways to really begin to, we've been fighting this war against cancer, as you know, for 50 years, and it's not one we're winning. So we need to open up kind of a new front in the war on cancer and get much better at early detection when cancers can be cured.
So which cancers can okay, let's talk about sort of traditional medicine before we get into, what you guys are doing that might change this whole thing. But right now, as it stands, there's various guidelines for early detection of certain cancers. Which cancers are those? And, tell us how effective those are right now.
Great question. So right now, today, we screen for three cancers in women: breast cancer, cervical cancer, colorectal cancer. We screen for one or two in men: colorectal and prostate. And then for heavy smokers, whether you're a man or woman, we have a low dose CT for screening for lung cancer in heavy smokers who meet that criteria. So all told, if everybody, if you look at adults over the age of 50 who are at elevated risk for cancer, those five screening tests are finding about 15% of the incident cancers in that population. So you can
Is that
see
right?
very quickly that's not going to do the trick.
Yeah.
We're not going to
Yeah.
shift the cancer mortality curve or bend the cancer mortality curve or win the war on cancer, finding 15% of the cancers at an earlier stage. And
You're saying out of the cancers that we can currently, with our current paradigm that we screen for, even though we have these guidelines and we're doing this in a lot of patients, we're only catching about 15% of those cancers
no,
early on,
of all cancers. So
of all cancers.
if you look at the population in the United States over the age of 50, and you look at all the cancers they're going to get based on the
Yeah,
epidemiology in the United States, those screening tests are only able to find, given their compliance and their performance, about 15% of them. So again, when I went to get my colonoscopy when I turned 50, I felt pretty good about myself. What I
right.
forgot, is that I was 10 times more likely in that very moment to be diagnosed with some cancer I wasn't even looking for. right? So whenever you're looking, so we live in a world of single cancer screening right now. We screen for one cancer at a time. We look at shadows and images, or we directly inspect tissues. And though that's quite limited, right? So you're only going to find those very few cancers, and you're much more likely to be diagnosed with one of the many cancers that we're not screening for than those. And then those are also limited because they have very high false positive rates. And many of the cancers, like early encapsulated prostate cancers or the early hormone positive breast cancers, people may be more likely to die with than die from. So those are the limitations of current screening.
Um, I want to get back to this idea of like the limitations of screening in terms of the all the different kinds of cancers there are, because I think I saw on your website, correct me if I'm wrong, that of the cancer deaths that occur on a yearly basis, 70% of those cancer deaths are occurring in cancers that we're not screening for at all, that we're
That's
just
right.
basically playing defense on. Is that right?
That's exactly right. So many of the deadliest cancers, stomach cancer, esophageal cancer, pancreas cancer, ovarian cancer, uterine cancer, we have no recommended screening tests for at all, liver cancer. And so it's kind of the classic streetlight problem where,
Yeah.
you drop your keys and there's a streetlight over here. So that's where you're looking. But
Yep.
all the deaths are happening over here in the dark.
Interesting stuff. So let's shift gears a little bit. We're gonna talk a little bit about Galleri now, which is the test. The biology behind the blood test that GRAIL is doing kind of has an interesting backstory. It
Yeah.
sounds like it was involved in trying to sort of minimize the use of amniocentesis. You want to tell us a little bit about the backstory there, because I think it's pretty interesting.
Thank you for asking. It's actually a fascinating story. So at Illumina, which is the biggest sequencing company in the world, the chief medical officer there was someone named Rick Klausner from the NCI. And they had a hypothesis that, because the mother and the fetus are sharing blood through the placenta, that we might be able to look at the mother's blood to determine whether there was a chromosomal abnormality in the fetus rather than sticking a large bore needle into the uterus in the amniotic sac and drawing out the fluid, because that carries a risk of aborting the fetus.
Right.
And so they did a study in 125,000 women, healthy pregnant women. And sure enough, they learned that yes, we can find the fetal chromosomes in the mother's blood. But there were 10 really abnormal cases where they looked at the DNA of these women, and one of the lab directors, a woman, and Dr. Klausner said, you only see abnormal DNA like this in people with cancer. Bring all those people back. And those 10 women all were found to have a cancer, many different types of cancer. And that was when the light bulbs went off within Illumina saying, we may have just found a way to find asymptomatic early cancer in people who have no idea they have cancer by looking at the DNA circulating in their blood. So they spun out GRAIL as a private company, and GRAIL raised a lot of capital to do some of the largest studies ever done to figure this biology out and developed this assay.
And that kind of brings us to what exactly sort of the technology is, because it's based on this concept of cell-free DNA. Talk about what cell-free DNA is. I mean, it's kind of what it sounds like, but why is it of significance?
Well, it's really important. So just so that everybody understands, all cells in our body carry DNA. And when they die or are injured, they release that DNA into your blood as long as there's access to the bloodstream. And so there's a lot of DNA that's circulating in our blood, and we call that cell-free DNA. Now, tumors, by definition, cancerous cells, are growing faster than our normal cells most of the time. And so when they die, they also shed their DNA into blood. So when you get a sample of DNA in someone's blood, it's a mixture of healthy cell DNA and tumor DNA. And GRAIL, when it was founded, did a very unbiased and open experiment. And they said, let's look at all this DNA in the blood and let's test all the available methods about how to read this DNA. We'll look at mutations. We'll look at chromosomal changes. We'll look at RNA. We'll look at proteins. We'll look at DNA fragment lengths. And we'll look at the methylation status of these DNA fragments. In other words, how are they methylated? Are the genes hypermethylated? Are they hypomethylated? And because there are very consistent patterns of methylation in cancer. These are all the hallmarks of cancer. And they compared all of these approaches head to head. And they learned that by far and away, the best way to detect cancer was by looking at these methylation patterns in these fragments of DNA.
You know, again, we've I think a nice way to think about it for people again to me is like methylation patterns. We talk about epigenomes. But really, what we're talking about is these DNA related fingerprints of cancer that we're using all of this information that we have to put together and say that when there's cancer in the body, there's these various fingerprints in the blood that you're able to pick up on. Is that a fair assessment?
That's exactly right. And that's why machine learning has been used, because we've taught these machine learning algorithms by doing these very large studies to recognize these very common patterns, these fingerprints that you only see in cancer. You almost never see these types of fingerprints in people who are known not to have cancer. And the other important thing just to mention, these methylation groups, these epigenetic patterns, they also carry another fingerprint, which is where in the body, what organ or tissue that signal comes from. So our GRAIL test called Galleri is a two-step test. So you sequence the DNA for these patterns, you subject it to a machine learning classifier that says that's a cancer signal or not. And then if it's a cancer signal, it goes through a second step that says we predict that cancer signal is coming from the ovary or the pancreas or the stomach. And we do that with very high accuracy.
Just curious, when you're using machine learning, you're using artificial intelligence. Obviously, medicine is one of the places where we're probably going to see the greatest impact of artificial intelligence. Does that mean that the test that you have, the Galleri test, is actually improving in real time, sort of because you're getting constant feedback?
That's right. So there's a certain way you have to do it. You can't just do it on an ongoing continuous basis because you need to revalidate and retrain. So So yes, that's exactly right. Because Gallery is now out there available as a lab developed test in the world, we've now done over 100,000 tests. We're using that data now to train the next version of our algorithm. And then we'll revalidate that. And then that'll be the next version of Gallery. And it will improve its performance by now having seen a much broader array of different cancers and different signals and in a lot more people.
How many cancers are we talking about right now that Gallery's able to detect?
Well, there are hundreds of types of cancer, and we're still grouping them. For example, there are 4 or 5 different types of breast cancer. We call breast cancer one. There are many kinds of
Yeah.
lung cancer. We call lung cancer one. So we're still doing a lot of grouping, but if you ungrouped everything, even a little bit, we're absolutely, with all the grouping, we're over 50 different types of cancer. If you ungrouped them, obviously it would be a much bigger number than that.
Right. Well, and that's obviously a big improvement compared to the 5 that you mentioned
That's right. And
earlier,
remember,
right?
again, as you mentioned, most of the cancer deaths are occurring from all these other cancers that we're not looking for at all.
Not that it's like a head-to-head battle, but I am curious, like if you take like a breast cancer, typical, the type of screening that we do today, what kind of, sensitivity that is compared to, the type of testing that you're doing with Gallery. Like if you go head to head, Where do you have statistics to say one's more likely to find that cancer than the other?
Well, we know a lot, quite a lot. I mean, again, it's really important for everybody to understand that the Galleri test is not intended to replace
Right.
existing single cancer screening tests. It's proposed to be a complement, kind of an adjunct test
Yeah.
to add to it. Because remember, these tests were designed very differently. So mammography is a great example. Mammography is looking at shadows from images taken of the breast tissue, and it's trying to find everything. It's trying not to miss anything. And in fact, of 100 women who have a positive mammogram, only about 5 to 6 of them will end up having breast cancer. So it surveys everything very broadly. Now, Galleri, because it's looking for a very common signal that's shared by over 50 or more cancers, we've done the opposite. We're trying to be very specific. In other words, they're focused on being very sensitive, and their positive predictive value, which means if you have a positive test, how often is it cancer? Their number is about 5%.
Yeah.
Our numbers are the opposite. So with Galleri, we will miss a lot of the breast cancers that mammography may find. But if we find a signal for breast cancer, the likelihood that it's going to be cancer is somewhere between 40 and 50%.
Right.
Much more, an order of magnitude better, because it's so much more specific for cancer. But we know that a lot of these slow growing cancers, like slow growing breast and prostate, that are found by imaging, and lung. Again, these nodules in the lung that low dose CT finds are often not cancer, and they're not going to
Yeah.
kill people. They're also not shedding a lot of DNA into the blood. And
Right.
so Galleri is not going to find those cancers that we worry about that we're overdiagnosing today.
When we talk about in medicine, we talk generally about these terms that you're using, like sensitivity, positive predictive value. We talk about specificity, but for the test as a whole, what kind of? Let's talk about positive predictive value. I think you mentioned it already, but let's define that and kind of give us again a sense of what that is with this test.
So again, the most important metrics for a multi-cancer early detection test are going to be different than the metrics for a single cancer screening test, right? A single cancer screening test, there's just one organ that they're looking at, and they want to be very, very sensitive. They don't want to miss anything, and they accept very high rates of false positives. So,
Right.
stool-based colon cancer screening, low-dose CT, mammography, the false positive rates are well over 10%.
Sure.
Okay. And we accept that because it's just a single organ and we know what those next tests are. For a multi-cancer early detection test, you can never accept that kind of false positive rate.
Right.
So our false positive rate for Galleri is 0.5%. It's 0.5%, an order of magnitude lower. Now, what does that mean? That means that if you don't have cancer, we are very unlikely to have a positive result. Now,
Right.
because cancer is very, it's only about 1 to 1.5% of the population has cancer. The positive predictive value is a very important measure as well, which is if you have a positive result, what's the likelihood that you have cancer? And again, for single cancer screening tests, that number is somewhere between 5 and 10%. Okay. For
Right.
Galleri, that number is somewhere between 40 and 50%. So an order of magnitude better. So if you're a doctor and you're sitting in front of a patient who has a positive Galleri test and a predicted location esophagus, that person almost has a 1 in 2 chance that they're sitting there with cancer right now. And it's serious business. You got to go look for that cancer because you're likely, to find it.
Yeah. So is there variability though in terms of the positive predictive values per different type of cancer within the Galleri test?
So the positive predictive value is really associated with that signal, that shared cancer signal. But
Okay.
you're right, the sensitivity is different for every different type of cancer because the sensitivity is related to how much DNA is being shed by those tumors. So let me give you an example. Pancreatic cancers. The deadly, fast-growing invasive cancers are shedding a lot more DNA, even in their earlier stages, than slow-growing encapsulated prostate cancers or slow-growing thyroid cancers or slow-growing breast cancers. So we're going to have much higher sensitivity. So we've done an analysis where we looked at a pre-specified subgroup of 12 of the deadliest cancers. And our sensitivity for those deadly cancers in stage 2, which is still curable, is 70%.
Wow.
Okay.
So that's remarkable, especially because you're talking about pancreatic cancer here, which, I mean, most people who are, in their 40s and 50s have heard about a story about somebody getting pancreatic cancer who was totally healthy and then they died 3 months later. I mean, I was even talking to a surgical oncologist friend of mine yesterday, and he wanted me to ask you about that specifically how is this going to benefit us there? Because that's what he's getting, that's his worst outcome patient.
That's right. Most pancreatic cancers are found after patients either have signs or symptoms. And when that occurs, it's usually too late. That means that cancer has already invaded into the biliary system or invaded the nervous system and has already spread beyond the pancreas. And so we already, in our studies and in the real world, have found multiple stage 1 and stage 2 pancreatic cancers. And the surgeons say they've never seen this before, and they tell their patients that it's like they hit the lottery,
Right.
because they took the Galleri test and we
Yeah.
found these.
So, there's also some cancers that are probably not going to be as good for Gallery. I mean, in a former life, I was a neurosurgery guy, and you have the blood-brain barrier. Those types of issues may confound some of those findings or make it more difficult to find brain tumors, things like that. Is that right? And maybe talk about some of the limitations.
Yeah, that's absolutely right, Buck. So, for example, we're very clear when we educate doctors about our test that we're not going to find brain cancers because most brain cancers are protected from the bloodstream, and so as they shed DNA, that DNA from those cancers is not going to get into the blood; it's going to get into the cerebrospinal fluid, and so we're not going to be able to find brain cancers. There are other very slow growing cancers like thyroid, some of the prostate, some of the breast that we're not going to find well. We will find the aggressive triple negative breast cancers very well. We'll find the aggressive prostate cancers even in early stages well, but the slow growing, more indolent phenotype cancers that people are worried about that we're overdiagnosing, we are not going to find those well. Some of the very slow growing urothelial cancers, the DNA is much more prevalent in the urine than in the blood. We find those, but not as well as some of the other ones.
Yeah. I'm curious too, like, I mean, I obviously because I think about the brain stuff a fair amount, but is there any thought on screening? I mean, the problem I guess is you don't really want to do a spinal tap once a year to test CSF and that kind of thing, right? I mean, any other potential solutions around that you can foresee?
There are, and we're thinking about them, and other companies are as well. There's some CSF that interacts with your sinuses
Yeah.
and can get into your saliva. So there may be other biofluids that can help us because you're right, getting cerebrospinal fluid from a spinal tap is not something that's going to be easy to do as a population screen.
So typically the idea with a test like this is maybe, is your vision that maybe you would do it once a year in addition to whatever other screening you're doing. Maybe you even started earlier than some of the other screening because it's pretty easy to do. I mean, what's the idea here about like how often to do it? And if you do it a certain number of times, does the sensitivities improve? Things like that. Maybe comment on
So
that for me.
so based on everything we know about the biology and the natural history of cancer, and everything we know about DNA being shed from these tumors and how that evolves, we believe that about a 1 year testing interval is about right. Now, we may learn as we learn more that that needs to be every 6 or 9 months. But right now, we think a year is a good way if you're trying to optimize the number of cancers you find in the population. Because what we're learning by looking at the DNA in the blood is that these aggressive cancers are moving pretty quickly, which is
Right.
different than what we often saw with staging. You know, when you're looking at imaging or feeling the cancer in surgery. So the movement between stage to stage is a little different than what we're seeing with the DNA. And so I think we're rewriting the textbooks as we're developing this assay. But you're exactly right that, you know, an annual screening interval is what we're recommending right now. And in about a year or two, we're going to have data from studies where we've done several consecutive annual tests in individuals. And we will get even more information because right now, all the performance, as good as it is just based on a one-time test in an individual. We haven't even begun to layer in the data within an individual, how their signal is changing over time. That may be much more informative than what your signal is at any given point in time.
So my friend, who you know, Alan Viglione, Dr. Viglione, um, he does some of these shows with me, and he's here in Santa Barbara, and he's the one who suggested that we touch base. And one of the things he mentioned to me is that he saw you talk, and there was a bunch of oncologists in the audience that really were not interested, they were not happy about the existence of this test. And frankly, when I hear all of the potential behind this test, it really surprises me. I mean, to me, this is like a very exciting potential way of saving thousands of lives. So why would the oncologists be totally against this?
Well, it's not, there may be some oncologists
Yeah,
that are not on board yet. It's very disruptive and very new. So we spend a lot of time with oncologists. Some of them have been founders and advisors to GRAIL from the beginning. And the
yeah,
oncology community largely has really embraced what we're doing. But remember, oncologists are not the ones who usually screen for cancer.
right.
And so they're not as familiar with all the issues around cancer screening. In fact, when I ask oncologists sometimes what is the positive predictive value of mammography, they say things like 30, 40, 50%, which is not at
Yeah,
all correct, right? Because that's not, they're used to treating cancer.
sure.
And again, we think that if we can find cancers before symptoms present in their asymptomatic state, and in earlier stages, there are many more treatment options, many of which are surgical and radiation and not drugs. And so that's also a difference. But we know drugs are moving earlier and earlier across many cancers. So there's a lot of excitement in the oncology community, but there are skeptics, and the
So what are
skeptics
the skeptics? What are they worried about? Like the ones
they're,
who are worried about it,
they're worried
what?
about well, how do we know that it's good to treat all these early cancers? Well, we know generally that for solid cancers, we've got enormous amounts of evidence for breast, lung, colorectal, others that when cancers are treated early, they have better outcomes. Even in the same stage, if you have an asymptomatic stage 3 and a symptomatic stage 3, the asymptomatic stage 3 generally has better outcomes. So we know that, but it has not been clearly and definitively established for every cancer type because
Right.
most of these cancer types are extremely rare. They're uncommon.
I'm guessing that part of the objection is they're getting positive Galleri results and from their primary care doc, and they're immediately getting shipped over to the oncologist, and the oncologists are looking at this and they have no idea what to do with it or how to interpret it because they're
Well,
not
I think
sure.
that's the worry. That's the worry. But in fact, in actual practice, when we return a result, like it says, Mrs. Smith has a cancer signal detected, predicted origin uterus, most doctors know what to go do, right? They go image the
Right.
pelvis. And then if there's a lesion found, then they refer them to the oncologist. But you've got to go make the diagnosis of cancer. So it's really important for the audience to understand what Galleri is detecting is a cancer signal in your blood and predicting where that cancer signal is coming from. You now have to go diagnose the cancer. And once the cancer is diagnosed, then the oncologist will know what to do with it. But it may not be the oncologist. It could be the surgeon. It could be a radiation oncologist.
Sure, sure. What kind of training are, so, obviously this is going into the hands of primary care docs. And part of the issue is like, they need to be trained on this stuff, right? I mean, if they get positive results and you send somebody for imaging, and if it's negative, what do you do? I mean, I don't even know what you would do in that situation. Maybe you can comment it, but maybe you could talk about, some of the training that's involved, and also as a follow-up to that, what do these people do if there's, they can't find a cancer in these people they're screening?
Well, let's go to this. So first of all, we have very extensive educational training that we do with doctors. And if a cancer signal, if you ordered a test, for example, and you got
Right.
a cancer signal detected result, one of our medical science liaisons who are in the field would be in contact with you within 12 hours about that individual case and seeing what information you needed. Do you need any resources? How can we help? We have experts at the ready to talk to you if it's a complicated case? So we have a huge amount of resource available to support the doctor if they get a signal positive case. Now, when you do get a signal positive case, let's just say that case, uterus, positive signal uterus, you do a pelvic CT and it's negative. Your question is, okay, now what do I do? Well, you've got a couple options. One, it could be that the lesion is too small and it's just not imageable. Imaging is not perfect. So you might bring the patient back in 3 or 6 months for a second image. You might just consider it a false positive right then and say, you know what, it's probably a false positive. We'll do Galleri again next year and we'll chalk it up to that. GRAIL also offers a free repeat test in those cases, and you might just repeat the Galleri test because sometimes it might be positive again, in which case you'd really want to investigate further. And then you want to talk to the patient to see maybe the signal is actually a cancer signal, but it's not in the uterus. It's in the spleen, or it's in the liver, or it's in the stomach, and we need to look somewhere else. So are there any other clues about where else to go look? And then every once in a while, someone will say, I feel very strongly that you may have cancer right now. Let's do a whole body MRI or a whole body image of some kind. But that happens pretty infrequently.
Um, how often do you find, well, I guess one of the questions I would have as a follow-up to that is if you have a positive result, going back to this idea that we were talking earlier, that in some cases, or not infrequently, we have cancer cells in our body that are being taken care of by the immune system. Is that part of what you think might be going on when you have a positive test followed by a negative test, or is it something else?
We don't know is the honest answer to your question. We really don't know. It's unlikely if a tumor is small and early and being addressed by the immune system, it's unlikely that those tumors are going to be shedding large amounts of DNA into blood. But the truth is we just don't know the answer to your question. I think we will learn that over time. But we're seeing a little bit of everything. We're seeing those cases where you have a negative workup. We're seeing, sure enough, 3 months later, 6 months later, they did find the cancer. Remember, imaging can miss cancers, right? Early cancers, and that happens not infrequently. We've had many cases where imaging was negative and then it became positive and the cancer was found.
Um, so tell us about any data that you have right now, or maybe some of the studies that are happening with regard to using Galleri in the clinical setting. Um, Maybe when you data to support what happens when you combine it with some of the standard of care screening that you talked about, which presumably that's the idea to do.
So the first study we did was called the Circulating Cell-Free Genome Atlas, which was a group of 10,000 patients with diagnosed cancer, newly diagnosed, and 5,000 adults without cancer. And that enabled us to really develop the test, validate the test, get to a new version, test it, and validate it again. Then what we did is a real world interventional study called Pathfinder. This was a seminal study in the field. It was 6,600 adults over the age of 60 from 6 or 7 centers around the country, like Mayo Clinic and Cleveland Clinic, Sutter Healthcare, Oregon Healthcare, and we had very special centers. And these were asymptomatic individuals. And what we did is we added Galleri to their standard of care screening. And we followed them all for a year. And what happened? Well, adding Galleri doubled the number of cancers that were found in this population on top of standard of care screening. And half of the cancers that were found by Galleri were in stages 1 and 2. So again, really remarkable finding in a real world population. It
Sure.
was safe. There were no adverse events that were significant. The satisfaction of the people who took it was high. Even when there were false positives, their satisfaction was very high. They were glad they did the test. There were false negatives. There were false positives, as you would expect. But we doubled the number of cancers found compared to standard of care screening, which is very consistent with some of our modeling that we've done and published. There's also a large randomized clinical trial going on right now in the UK, in the National Health Service, of 140,000 adults over the age of 50 randomized to standard of care versus standard of care plus Galleri. And we're already almost done with the second year of that study now. And so that will be a huge study. We're also following all the tests that are being done in the real world, over 100,000. And we're seeing findings that are very similar to what we've seen in our trials, which gives us a lot of reassurance and confidence that the test is performing well.
Do you have any sense, and I'm sure you guys have looked into this, that if you get sort of accepted into the standard of care of screening, even just say in the United States alone, like what is the potential in terms of lives saved?
So we've estimated that, and this has all been published based on models, pretty conservative estimates. But, as I mentioned, today, if you just look at adults over the age of 50, there's, I don't know, well over 1 million cancers that are diagnosed every year. And if you added Galleri to our standard of care screening, instead of only finding 15% of the cancers by screening, you could now find 50% of the cancers by screening. And 75% of the deadly cancers you could now find by screening. So if you add that up and you say, okay, what is the impact on life expectancy or the number of deaths averted, that calculates out to about 100,000 deaths averted every year, which is about a 39% reduction in the expected deaths over the next 5 years. That is about the same magnitude as everything that we're doing in cancer. Everything. If you add up everything we do in cancer, screening, diagnosis, treatment, hospice, surgery, everything, we're averting about 100,000 deaths a year. And you could have that same magnitude of benefit if we just adopted Galleri and everybody took it based on the models.
Which is, of course, now like, anybody listening to this wants to probably, think about getting Galleri tests. It's not something that's currently covered by insurance.
There are some
Where are
insured,
you in that
there are some,
process?
there are some who cover it. Not many. There are many self-insured employers who are providing it to their employees and their payers. So we do have some coverage. There are also some life insurance companies that are providing it as a benefit to their care, their covered lives. But we are in an accelerated approval breakthrough designation with the FDA, and we're hoping to get FDA approval within a few years now. And then we hope to get Medicare coverage as well. And we think once we get the FDA approval, that many of the payers will come along. Right now, we have New York State Department of Health approval, CAP-CLIA certification. So we're available out there, but it's most people are paying out of pocket right now. if they
Yeah.
don't have payers coverage.
How much does it cost typically right now?
So typically, if you're just walking in off the street to your doctor, it'll cost about $949. But if you're part of large group practices or large concierge practices or other health systems that we have partnerships with, there are discounted rates that are available for them.
This is well, this has been fantastic. One last question for you though. That's because you mentioned the insurance thing, the life insurance. Probably makes some people wonder if this information should go into certain people's hands.
Well, we've
And
been crystal
yeah,
clear that
yeah,
if we're going to work with life insurance companies,
right.
it's not to be used in underwriting risk at all.
Sure,
Our
sure.
test doesn't tell you about your cancer risk. It tells you about whether you have cancer right now. And so it is being given as kind of a gift to them, to their life insurance. It's not being used to underwrite their policies at all. We
Got it.
would never engage in that, and
Yeah.
have been very clear with our life insurance partners. They don't want to do that either. So many life insurance companies now offer things like vitality programs, and because they're highly motivated to make sure their policyholders live good, healthy, long lives, and so they're giving gifts to their policyholders to try to help them, and some of
Yeah.
the life insurance carriers are now giving Gallery.
Fantastic. Well, Dr. Ofman, Josh, thank you so much for being on Sapio with Buck Joffrey. It's been just a really incredible technology and the best of luck with it.
Well, thank you so much. Pleasure to be here.
That's it for this week on Sapio with Buck Joffrey. Now, if you like what we're doing here, make sure you like, subscribe, and share because that's the way we're going to keep all of ourselves and our friends and family healthy.